try to solve a numerical problem which is related to the Bohr's model of hydrogen atom and how it explains the spectral lines or the spectra given out by it may be an emission spectrum or an absorption spectrum given off by the hydrogen kind of hydrogen atom or species which are similar to hydrogen atom containing one proton or two protons but having only one having only one electrons around it. So the question says, what is the wavelength of light emitted when the electron in a hydrogen atom undergoes transition from an energy level with n is equal to 4 to an energy level with n is equal to 2. So it goes to the fourth shell and it comes back to second shell. So how much like electromagnetic radiation will be emitted? What will be the wavelength of that electromagnetic radiation? That's what the question is saying. So the first and the concept that will come to your mind while solving this equation is that according to Bohr tried to give out, according to him, the energy was quantized, right? The electron in a hydrogen atom cannot stay in any shell, but but it will stay at only those places where the energy level is this much. It will have some value, some specific value. In other words, it was having a value of, it will be a multiple of 2 into 2.18 into 10 to the power minus 18 joules. No matter where it stays, an electron around in a hydrogen atom, its energy level will be multiple of this. It's the energy is quantized. The mathematical expression for calculating the energy level of an electron at the nth shell is given by En is equal to minus of RH by 1 n square by 1 by n square 1 upon n square, right? And the value of the Rydberg constant is 2.18 into 10 to the power minus 18 joules. So here we will calculate. So suppose it was in the fourth shell. So it was in fourth shell. What will be the energy in the fourth shell? It's given by En equal to RH minus of RH 1 by n square, where n equal to 4. So when it comes to the second shell, its energy will be same expression, but 1 by 2 square, right? So what is the difference in energy? Whatever energy was there, so it will be energy in the final shell minus energy in initial cell, right? So this will give the difference in energy. The final shell. So if the final shell is what? So it will. So if we put the value of this in the F shell or in the final shell, what will be energy? Something like this. What will be energy in initial shell? Its energy will be something like this. So taking the RH common, what is left for? 1 by nf square minus 1 by n square. This is what is left out. Energy in the F shell, in the final shell will be given by this expression, 1 minus RH by 1 nf square, right? So and energy in the initial shell, that means in the fourth shell, will be given a minus RH of 1 by n square, means 4 square, right? So if you so in those two in those two terms, RH is common, so you take out the RH common. What is left for? 1 by nf square minus 1 by ni square. The square of the final shell minus square of the initial shell, right? The nth shell. So here the value of n is 4, or the final is 2. So 2 square minus 1 by 4 square, 16 square, 1 by 16. And what about this one? So what is the energy that you're getting? This is the energy difference in energy while staying in the fourth shell and coming back to the second shell. So this difference in energy will be released as electromagnetic radiation, right? It will have some energy, this energy with this, and the expression of that is given by E equal to h nu, right? E equal to h nu, Planck's constant multiplied by the frequency. This is the energy of the photon. Each photon will possess this much energy for this difference, for this much of energy. A photon will be possessing this much of energy, and and this again is given as h into nu, frequency. Now whatever frequency is, according to the relationship of an electromagnetic wave, frequency is equal to c by wavelength. C is the velocity of light in the vacuum divided, or electromagnetic radiation, which is 3 into 10 to the power 8 meter per second, divided by the wavelength. So on the left hand side you have Planck's constant. the velocity of the electromagnetic radiation, that is 3 into 10 power 8 meter per second, and the wavelength. And on the right side you have this, you have all the numbers, all are constants, so you can easily calculate the wavelength. I'm not calculating the wavelength, so this is the way we're going to calculate the wavelength of the light emitted when an electron is transferred from n equal to 4 to n equal to second shell, n equal to 4 to n equal to 2 shell. This much energy will be given out in the form of electromagnetic radiation, and this is equal to h into energy of one photon given by the product of Planck's constant and frequency. Frequency is c by 11, c by lambda. So in this way you can calculate the wavelength.